Okay, welcome everyone. Now we are holding fourth collective meetings. We planned 5 of them, if you remember, and probably we will do one more. Recently, Eden returned, and I talked to him. So the presentation date will be the same. We will not extend overall course. But maybe we can use some time from writing paper. One thing maybe you can check whether you have enough thing to write some like short paper, or if you don't, maybe instead of writing this short paper, you can do more progress, something like this. Okay. Is there any question before starting? Okay, then 32, project 32, theory. I should give access. Just wait. I'm forgetting. All participants can share. Okay. 32 theory.
Good morning.
Can you share your screen, please?
I'll share the screen. Desktop share. Oh. Do you see my screen right now?
Yes, and I see 3 names. These 3 names contributed to presentation.
Yeah, all 3 of us have contributed to the presentation.
Okay, floor is yours. You have 10 minutes. Thank you.
Thank you. I'm Seaman, and my other groupmates are Ditya and Christian. And okay, so basically this is something that we mentioned in the previous meeting, but basically we have the QPE circuit, and we run the circuit, and we have this count over here, and then we can plot this probability curve onto it to do a curve fitting. This can estimate, like the curve fitting can estimate the theta which we're trying to find the phase. So in this example, the estimated one is 0.333, and the theta that we had used was 1 out of 3. So this is about 3 decimal places accuracy. Okay, so what we have further worked on right now is that we have been calculating like the root mean square error. So in this example, I ran about 10 for each example, and I varied the number of shots that were used. So this is about 100 shots, this is about 1000 shots. And then this is the log root mean square. Our advantage in this method is that firstly, we see that it has a much lower error. It has much lower error with the same number of qubits compared to the naive traditional method. For example, in the naive traditional method, using only 3 recording qubits, it would be this value, which is 0.0625. Log of this would be negative 1.20. We can compare it to our experimental results, and we can see that even with just 100 shots, it produces a lower root mean square error. We also calculated the Cramer-Rao lower bound. So basically, we can compare our experimental results to the lowest mean square error which this method can produce. Over here, we can see that there is a bit of like a cutting through through the lower bound. This is likely because my sample size is still quite small at only 10, but I'll be increasing it to maybe 30 or 50. As for the Cramer-Rao lower bound, this is something that Christian will be talking about later on. Basically, our method allows using less qubits, although we need more num shots as a trade-off, to achieve the same number, the same accuracy. The circuit depth of a QPE is furthermore proportional to 2 to the power of n, where n is the number of recording qubits. So this means that using less qubits, it allows us to have exponential savings in the depth of the circuit, which is especially useful in this NISQ era. And this next portion is Christian's.
Just Simin, I would like to add that it's useful also for the fault tolerance area. If you save the depths and layers, and you get less layers, so you can have even smaller size of the surface code. So you also will reduce the number of physical qubits very meaningfully.
Christian?
Okay. Can you hear me?
Yeah.
Yeah, okay. So as Simin said before, my main contribution in this project has been from the mathematical part, and of course, to try to get the Kramer-Rao lower bound. So basically, as Simin said, we have been working on what we call maximum likelihood estimator according to our probability function, and the information of the estimated phase comes from the distribution probability in our case. So go ahead. This same information can be obtained from what we call the log function of this probability distribution. That is what I'm showing here. Of course, as in the previous slides, if we have two different phases to estimate, so the accuracy will be according to the histogram that is here represented by the points obtained from the circuit. So basically, the accuracy is according to the height of the different histogram of the recording qubit we have. After this analysis, an important mathematical point is to get the Kramer-Rao lower bound. For doing so, we computed the Fisher information for a single shot. That is the equation you're looking for. You're looking at the slide. And after computing this, we saw that the Fisher information in terms of the parameter theta, that is the information we want to get, is like a constant, as you can see in this plot. Okay, so the variation with respect to the parameter theta is very small, and taking this into account for the Kramer-Rao lower bound. Next, please. We can get like the lower bound shown by Simin to compare with the data according to this expression that is 1 over the total Fisher information. Here is plotted the square root of the total Fisher information. That is for independent shots is the number of shots n times the single Fisher information. So as Simin showed before, this is like the behavior we get for the lower bound, and now we are going to match the experimental data given by the simulation from Simin to this mathematical analysis to get more information about the post-processing we are doing.
And for effective results and comparison, to substantiate our work, we make it pragmatic in the real world scenarios. We objectified a direction for comparison. To present a pedagogical review of quantum phase estimation and simulate the algorithm to numerically determine its scaling in circuit depth and width. From what we read in previous attempts, we could move along the same ideology that they did. We review quantum phase estimation algorithm based on the same measurement operation, but the measurements are not random and the classical post-processing can be done efficiently. We simulate these algorithm and determine its complexity, circuit depth, and circuit width for various sizes of input. We improve upon this phase estimation algorithm by considering inference across multiple qubits. We show that this technique requires asymptotically fewer measurements and in turn has a correspondingly smaller circuit width and depth while still allowing efficient classical post-processing. These previous works compare the circuit constructions for Kitaev's phase estimation algorithm and work for how does the optimized estimation algorithm offers an asymptotic improvement in the number of measurements required to estimate the phase with exponential precision? Or how does the corresponding quantum circuit scale in terms of depth, width, and qubits can occur in parallel in a given time step? They define the depth of a quantum circuit as the number of time steps where gates on disjoint qubits can occur in parallel in a given time step. Here we assume that a given n qubit gate takes one time step. The width of a quantum circuit is the number of qubits. The size of quantum circuit is the total number of non-identity quantum gates. We analyze the circuits given different computing settings to emphasize trade-offs in depth and width depending on resource availability, and when using an M-mode node cluster of quantum computers, the faster algorithms requires essentially how much time. Next slide, please. The probability of success of the Grover algorithm and phase estimation measured by the QPE algorithm were found to exponentially depend upon the error probability in the noisy channels, but only linearly dependent on the number of qubits. Perhaps we study the impact of incoherent noise in QPE, modeled as trace-preserving and completely positive quantum channels. Different noise models such as depolarizing, phase flip, bit flip, and bit phase flip are taken to understand the performance of the QPE in the presence of noise. The simulation results indicate that the standard deviation of the eigenvalue of the unitary operator has strong exponential dependence upon the error probability of individual qubits. Furthermore, the standard deviation increases with the number of qubits for fixed error probability. This could be used to simulate the behavior on commercially available quantum computers. To perform an appropriate evaluation of such algorithms, particularly those aimed at possible quantum advantage, it is necessary to carefully model the noise, analyze its effects on the algorithm, and make a validation via experiments, namely using quantum systems. Another lucrative direction was considering how the algorithm reduces the number of samples and thereby the computation time for Monte Carlo methods. We hope to extend the method so that it can be used for actual noisy computers and then give an experimental demonstration on a superconducting quantum device. Thank you, and we would like to welcome any queries or comments from the audience.
Thank you.
Abu, I would like to
Yes.
put your attention. Simin, can you please return to the graph that you showed of the comparison between the Fisher and the Kramer row and your actual data? I would just like to emphasize here this method. There is some noise from someone put an. Oh, thank you. So can you return to? Yeah, thank you. So this slide is very, very important because it's showing that in the traditional method of the QPE, there is some MSC, some inherited error inside, and the Kramer lower bound is from the estimation theory world. It's telling you what could be the best error that you could ever get with any estimator in the world. And they are showing here is that their estimator is very close to the theoretical smallest MSC possible, and it's much below the traditional method. So I spoke with Eden and Yuda about the work of the group, and we aim to publish this not in archive but in physical review, because this is very important. It reduces, for the very good resolution, you get exponentially smaller depths. There is very serious work that's done here, and I didn't tell the group yet because it's new, and I talked with Eden today, but we plan to publish in physical review and not in archive.
I think you can do both.
Yeah, why not?
Archive is just technical report, just first saying we have this result to the community, and then you can submit the journal. But of course, it's up to you. So this is success of this specific group, correct?
Yes, this group and also the app group, which can combine the applicative part of this article. Anyway, Yuda, our CTO, is very impressed from it, and I think it can be very,
very nice to have such outcome. Yeah, congratulations.
Yeah.
Okay.
Thank you.
Yeah, thanks. I don't have any specific question from the audience. Do you have any question? Ron, you expected something like this, or it's also surprising for you?
It's not surprising actually, because this is something. This method is something that we developed in Classic few months ago before the course started. This using the work of this group, we could examine it and analyze it further and to actually see it happening.
Well, this group was also lucky little, it seems. Okay, now we can continue with the application group.
Thank you, Thomas.
Ira, you can share.
Yeah. Am I audible?
Yes, we can hear you. You
Can
can,
share my screen.
we see your screen. We wait your presentation.
Can you see my presentation?
Yes, I see two names. These are the people
Okay.
contributed to presentation. Correct?
Yes.
Okay.
Yes.
Thank you. You have 10 minutes. Floor is yours.
Sure.
Thank you.
Okay. Okay. So we are from the application part of the quantum phase estimation group. So, so the last presentation we talked about the theoretical understanding of quantum amplitude estimation to perform option pricing on quantum computers, and we also used classic SDK to try out various building blocks of this quantum amplitude estimation algorithm. We looked at several functions like state preparation, composite Grover function, and also the quantum phase estimation algorithm. So today we are trying to use these specific things to implement option pricing using the classic platform. So this is what was done last time. We are interested in the amplitude A. So we use the Grover's operator to encode this amplitude as a phase theta, and A is related to theta as A sine square theta. So once you have this phase theta, you can just use the quantum phase estimation algorithm and then do the measurement on the register, the estimation register, to get the value of Q. Once you know Q, you know theta, and once you know theta, you know A. So this is what was done last time, and this is the quantum amplitude estimation circuit. So today we are specifically using this for option pricing, and the first step is loading the distribution, that is loading all the possible spot price paths. So PI is the probability distribution of the option prices, possible option prices, and for this particular presentation, we'll focus on the log normal distribution. So this is the payoff function what we are going to use. So a max of 0 I comma I minus k. So 0 if the option price doesn't reach the strike price, and I minus k if the option price crosses the strike price. K is the strike price here, and you load this psi becomes phi 1 after you convert this psi n to this state phi 1. So it's easy, just you have to use a quantum comparator circuit. So that was discussed long ago. And once you do this, uh, you have to apply some rotations on this phi 1 to encode f of I, that is the payoff function, to this state phi 1. And then you do the probability measurement on the good state. The good state here is the state with the qubit 1, because I greater than or equal to k is the one where the option contract gets executed. So this is the probability we are interested to calculate through the quantum measurement, and this expression has this term sigma pi into I minus k, which is the expected payoff. So first we use the for the inbuilt model of classic, and the first step is to tell how many qubits are there. So there are 3 qubits, so showing that there are 8 possible price paths, and mu is 0.7, sigma is 0.13. This is the mean and the standard deviation of the log normal distribution, and I just load the log normal distribution, and then set the threshold value to be 1.9, which is the strike price, and the finance function input will have this European call option, which I defined in the previous slide, that is maximum of 0 comma I minus k. So the strike price is 1.9. Whenever the strike price is reached, the option gets executed. Um, so yeah, so once we load the distribution, and once we say that our finance, the function used is the European call option, then we just have to construct the finance model. This is already an inbuilt class of classic. We just state that the distribution is log normal model with the parameters already defined, and the phase port size is the size of the estimation register, and the finance function is basically the European call option. And we synthesize this circuit, and for this we get, and this also to note that construct finance model also has this best fit method, which I'm going to demonstrate soon. And this is the results what you get. that the estimated result is 0.17, and based on the theoretical results in the paper, it's around 0.12 or 0.13, I don't remember. So around 0.1756. This is the expected payoff of expected value of the payoff. So this is using inbuilt construct finance model of Classic. So now we are also planning to develop a model for finance model from the scratch. Since the previous since the previous model here allowed only for two distributions, log normal model distribution and also a Gaussian distribution. Here we have tried the log normal distribution. So here we are trying to, here we can, using the state preparation function, we can ask the user to input possible price paths with defined probabilities. And once we have this, this is just different components which we can use to build a option pricing model from the scratch. So this, we have the state preparation function. Then we have the amplitude loading function. What does this do? So this is basically define the payoff. So, for example, if you look at this breakpoint list here, 0.5, 3.14, and 5, it means that the strike price is 3.14. Between 0.5 and 3.14, your offset is 0, slope is also 0. So which means f of I, which is a linear function, ax plus b form, so that is 0. So between 0.5 to 3.14, you won't have anything. And between 3.5 and 5, you have this payoff function. So this is the payoff function part. And then you have the amplitude estimation part. So the next goal is to put all these things together and build a finance option pricing model on our own from the scratch. So once we have this, so we can use the best fit method of post processing to see how the expected payoff can be obtained with lower lower circuit depths and or widths. So this is the main purpose of this project, is to use post processing to realize how can this be useful to estimate accurate expected payoffs using lower circuit depths and widths. So this is exactly the post-processing function I was talking about. So here we are using the best fit method. This best fit method was used in the construct finance model, which I showed earlier. So just to demonstrate the difference between some methods, like there are two methods which I found on Classic. One is the best fit method and the other one is the max likelihood method. So I'll just show you. So this is the quantum amplitude estimation code. So here we are interested in amplitudes of the good states. So the good states here are those for which this expression is satisfied. So A register has 2 qubits, B register has 2 qubits, and all those states for which A is equal to B are my good states, and I'm interested in the amplitudes of those states. So here there are it's a 4 qubit register, so it can take it can take 16 possible amplitudes. So these are the amplitudes, and I know that the good states here are basically 0.25. This is the state 0, 0, 0, 0, and here of course A is equal to B. And similarly, we have other good states like 0, 1, 0, 1, 1, 0, 1, 0, and 1, 1, 1, 1. So these are the good states for which A is equal to B. And so here you can see this 0.25, this 0.25, this 0.25 are all amplitudes of good state, but here this 0 is the amplitude of good state. I just changed, I put 0.25 here, but this 0.25 is not the good state amplitude. So the expected result after the amplitude estimation should be 0.25 plus 0.25 plus 0.25, that's 0.75. And I run the quantum phase estimation algorithm, and I use the maximum likelihood method, and the results what you get, I've already just to save time, I've already shown it here. So this is the result what you get when you use maximum likelihood method. So you get 0.5, and 0.5 is not nowhere close to 0.75. But if you change the code slightly and if you use the best fit method, here this is the change, here best fit, and here it was the maximum likelihood method. So if you use this method, the execution results were almost accurate. So I got 0.744. So in the next, this is the difference between these two methods. So in the next presentation, hopefully we try to build this model from the scratch and use this best fit method of post processing, post process function to accurately demonstrate the expected payoff. So this is for it, for this presentation. Any questions?
Okay, Viraj, thank you. I don't have any specific question from the audience. There is any question? From Project 32, I see two more names, Junior and Akome. They didn't present. Ron, they are active or?
Which one?
Junior Tad Jegue and I think Akome Rugimeya also.
They are not here in the meeting?
They should also present, and if they don't present, because last week I clearly said, yeah, everybody should present and show themselves. So
yeah, their problem.
But they also have a lot of minus previously. Potentially, they can be excluded from the course. Okay. Okay. Thank you, Project 32. So I think Asif wants to go also, one of the first. David, it's fine.
Yes. Can
Continue with Project 27 because David also wants to.
Okay, maybe he can continue. I can personalize it.
Asif, you are in hurry or do you have time?
Not that much area. Yes, I have time. I can present later after him.
I mean, if you are in hurry, let's have you.
Can we limit time? Since everyone spent more than 10 minutes. I mean, we're waiting forever. I mean, can we limit time? People spend 15 minutes almost.
No, I'm checking time. It's 10 minutes usually. And I'm appearing after 10 minutes. David, are you in hurry? Okay, Asif, let's continue with you.
Okay, thank you. The screen is visible to you. My screen is visible to you. Hello.
I see your desktop. Not
Oh,
presenting.
wait. Let me. Just a little. Yes. Is it visible now?
Yes, not full screen, but we see it.
Okay. Yes, I'm going to bring full screen. Hello. It's present. Is it okay now?
Yes, I see three names.
Okay. Thank you. Okay, thank you. Okay, I'm
Okay,
going to
Asif,
start
I
my
will give you
presentation.
9 minutes, okay?
Okay, no problem. Hello everyone, good day to you. To this presentation, I'll be presenting Project 27, Q&A algorithm implementation. I'm Asif Sir. My other team members are Ashmi Gupta and Roman Lerner, and the mentor is Tal Michelle. So here I'll be implementing hybrid network for classifying the means dataset, which happens to be a image-based data and an image-based numerical dataset. So let's continue. So what I'll be covering here? I'll be covering here what we have so far achieved here and what's challenges and obstacle and what the next step we'll be going to take. Let's see the quantum neural network. Let's recap about the quantum neural network. How is it going to work? So more like the classical neural network, it has got all the things. It has the feature map. So in the classical convolutional neural network, we have the feature map. So in the quantum neural network, we have the equivalent feature map in the quantum space. And in here, unlike the classical space, in quantum neural network, we have the ansatz that consist of quantum circuits that would be doing the operation equivalent to the classical neurons. And there, the additional thing that does not exist in the classical neural network, classical convolutional neural network, is the measurement part. And what is measurement will be doing here? It will be measuring the qubits and transforming it back into classical human readable data. So let's see. So how far we have come into our projects. So these projects, we need to decide on the architecture, quantum neural architecture, which quantum neural architecture we're going to implement. Then we have got to encode the means data set into our preferable quantum space. And then there will be quantum layers that need to be interfaced equivalent to the classical neurons. And then we are going to have the measurement. So previously we were in the week 4 to 5, and we have decided on some encoding method. And then before this presentation, we were working on the quantum neural network. However, due to some limitation, we could not progress much in this episode. So we required some update in this state to do some better encoding system that is more scalable and preferable with our preferred quantum architecture. So here's about we have revolted the quantum neural architecture. We have decided and modified some of the architecture part we have previously decided on, because the thing is we could not just cope up with the previously agreed upon neural network architecture. Why? Because previously we had an image. Let me show you. We have an image that was 18 by 18, 8 by 8 pixel, but it was too much. Like it was like 64 pixel. It was too much to work on quantum circuit. So as our mentor suggested, we should have it reduced to 4 by 4. So in the previous form, we had this 8 by 8 pixel. So, but it was not possible to work with a quantum neural network. So we had to backtrack. And rebuild our whole quantum neural architecture. So now we have generated a transformer method that can reduce our image to a 4 by 4 pixel. That means it has 16 pixels, and that's an example of a reduced image. It's not possible. Maybe you can answer why I can't just plot it. It's not possible to plot it around because it's too much smaller to plot it, but it can be used to do computation. So that's our now agreed upon images of 4 by 4, let's say 16 pixels. So that's the new. So how did you? So we have got a transformer that can reduce it for 16 pixels. Now how are we going to encode it into a quantum space? How are we going to encode it with angle encoding scheme? So all of us, the team members and mentor, we have decided to encode 4 pixels per qubit. How are we going to do that? We can encode it. We can rotate it first along x-axis, then along y-axis, and along z-axis, and then again along x-axis. So there's like this is the circuit that's representing this qubit encoding 4 pixel in just 1 qubit. Or what you're going to do in future. Now, I know there's not much we have done because we have got some arrangement or organization issues, so we could not do much. So hopefully we want to implement our quantum layer that will be acting as a quantum neuron, and this quantum neuron requires the unitary matrix. So we haven't decided on how we're going to do the unitary matrix operation. So, and also there's some optimization issue. This neural network unitary matrix parameters had to be optimized. So we have to integrate with the classical optimization scheme like the atoms. We are prepared to work on atom gradient descent. So that's our future plan. And the challenges that we have faced is about like extracting. So we have encoded so far we have encoded the classical images into quantum space. And thing is, as I previously mentioned in the QNN architecture, we need to transform it from quantum space to classical space to understand it, to see that it has been classified correctly. So that's the scheme that we haven't actually devised. How we're going to do that? Maybe we may devise some other plan. And also another thing is how we're going to optimize or update the parameter of the unitary operation and work with the classical optimization method, and how we're going to update it. So that's the resources that we have so far working on, and some other papers that there are other papers that we have taken into account to discuss on the encoding scheme, but we couldn't actually just didn't bother about adding it into the resource board. And our goal now, the main goal was about to classify the means data set with a hybrid quantum neural network. So currently we're resolving the quantum layers neurons calculation and integrate with quantum atom optimization, and also placing the convolution and pooling operation, which is so much important for since we have an image-based data set as quantum circuit. And what is our short plans? What is our short-term plans? Short-term plans is to encode the unitary matrix and its parameters into the neuron, and the optimization scheme that we have decided on. Thank you, everyone. Is there any question?
Okay, thanks, Asif. You have one missing report, like collective meeting, overall progress. You should do more, Asif. I don't know what to do.
Yes, because I know we could have done this in this episode. We could not do much because we have some organizational issues.
Previous weeks are also, one is missing, the others are not like sufficient enough. Is there some difficulties about the subject, or you have some difficulties for your group?
Yes, we have some organizational issues. How we're going to do it? We could not match up the meeting timing. It was much, but we have decided, we have sorted things out. Yes, last week. So I think we can just space ourselves out from the future.
Okay, you should do more progress. I don't know, because there are also some individual reports are missing. So you should really do more. Asif. So Guillermo in the chat, you can check. Maybe he offers some help. You can contact him. It can also help. Is there any question for this group?
No.
Okay, thanks, Asif.
Okay, thanks.
I suggest to talk with Guillermo. Okay, we can continue with group 31.
Yes, sir. This is Bill. I'm prepping the presentation right now. Since we don't have very many slides for this presentation, I'll
31.
Yeah.
Yes,
31.
31.
I'm sorry.
Okay.
Never mind.
Can you see my screen?
I'll stand
Yes,
by.
yes.
Thank you.
We are seeing.
Yeah, so I'm ready.
Okay, you have 10 minutes.
Yeah, so basically we have some challenges because we lose our initial mentors and we're new mentors. So I'm gonna go through everything so far. For this presentation, most by me, because we have time meetings, I show you what happened in our group. It's not moving here, what happened? My screen not moving. Here we go. Okay. So we have a great plan in the future here. That's a problem here. Basically, we're trying to make something better than growth algorithms for structured optimization search algorithm here. So idea would be how to make a better with structures like a constraint satisfaction problem. So our idea is create a quantum backtracking is better than classic backtracking. So we try to make some progress. We have some presentation before. An idea would be we try to compare different search algorithms, classic search algorithms for the Sudoku, and classic backtracking for Sudoku, and also quantum globals algorithm and quantum backtracking. That's the best thing we want to do. So hopefully much better than the classic backtracking. So the idea here, the growth search algorithm is really special case of quantum backtracking for complete graph, right? If you have complete graph, the quantum backtracking become growth search algorithm. And both of them use the diffusion operators to perform for different nodes in the trees. So we have major reference here. Our main idea would be use a quantum walk speed up for the backtrack algorithm here. So here we achieved so far. So we went to the boot camp, then we had a couple of presentations. The idea would be the bench and I should be implement the quantum backtracking, and then the crystal will focus on the classic. And then we'll do some theoretical analysis. The problem here, we can't diverge, and the bench kind of stop something. It couldn't finish much about quantum walking algorithm here. Crystal focus much about classic. I mean, we should work together for the quantum backtracking, but it's not working well. So idea we have some challenges here. So we try to work together to finish up because our original mentors couldn't continue because happened in the over there. And we decide continuous, and we on the way here, our last another group members never contributed afterwards. I mean, she just disappeared. And in the meantime, the crystal kind of focused much on her stuff. I mean, the classic algorithm here. And so I try to make sure everyone works together here. So we couldn't meet it because we meet the Eric one time, and because I wasn't travel, so really not much come back from our mentor either. So I tried my best here. So I do this contribution for this time here. So what happened here individually, Crystal still focus on her.
So David,
Yeah.
maybe you
So
can.
I'm stopped here. So how many minutes I have? So I'm just showing you what happened there, and I'm focus on my contribution in couple few pages. So
wait. So
yeah.
Three people are active now.
Yes.
And you will modify your original plan maybe based on what you have.
Yeah, I show you later on what's happening our planning in the future. So I show what I have done now, and I show you what's next step.
But these three people still actively working, correct?
But it's working, but seems we do different things. We don't work together.
So three different projects, kind of.
No, it's what happened there. Crystal just focus on the everything classic. I'm saying, okay, work together. We are difficult to implement the quantum tracking. It's so hard. I mean, it's not easy to implement. I mean, but they say, okay, I'm do the Crystal say I'm do the classic, right? And Vance just say I'm do the network X. Now she come back with the very beginning here. So I'm trying to pick. I will do all my stuff. I mean, I don't need them basically. I mean, I'm just tired of that. Anyway, so I'm showing my step here. So I willing to do my own group. I mean, if nothing works here, so I make a big progress here. I'm kind of I'll show you later what I have done here. So I did I did Global's algorithm here works, and also I did a quantum backtracking. I mean, not for Sudoku yet, but it can work. And also I show some example later on here. So basically that's what I'm doing now. So show you here the one I did Grover's Sudoku algorithm here. Before the IBM only do a 2x2. So I work with the 4x4 Sudokus. The 9x9 is hard because there are not enough qubits work on it now. So really hard. So I'm doing the 4x4 for now. Maybe in the future here we do 9x9, the real Sudoku. So here is the example I show you here. We have a board here, and the asterisk is missing value here. So I running my algorithm here. So I get my estimate here. So 31, 23, 23, 31. That's the missing values in the Sudoku, right? 1 to 4. So I did that. So that worked here. And so pretty good performance. So I did this one myself here. And then also quantum tracking. It's the two reference here. They don't give any details. I mean, most theoretical. The second paper, it seems they're practical, but they don't give any details. So I had to try to figure it out, look at different open source, try to put together here. So I finally get the quantum backtracking trees works most time here. And then for any problem here, for any constraint satisfaction problem, so you need to provide accept function and also reject function here. So I show two examples here. So one thing here, how detect solution here. So we have a tree here, and then we create a tree here. There's only 0, 1, 0, 1, 0, 1 here, right? So it won't be found node 0, 1, 0. And I don't picture here. So yeah, so we define the acceptance function and also reject function here. So I didn't show example here because the much here. So what happened? You run it, And we got also here, so 0.0023253 is the probability we found nodes. So definitely it's not, right? So that's say we just work here. And here we try to find for the quantum tracking, what's in the final solution here. So not just detect. So here example here, try to find nodes 10111. So we define a set function, reject function here, then we run it, the quantum tree here. And then we have 7 qubits, and we find out 111 is found. So it's just preliminary. I haven't been able to define the accept and reject for the Sudoku yet. That should be fine. I mean, I need to define a function here, and I should be able to, for the quantum tracking, should be able to do the same thing here for the globals algorithm for Sudoku. I mean, this should be next time I show this one here, how to use the quantum tracking. Solve this problem here. Hopefully we can do 9 by 9 switch here, but for now we're going to do the globals for 4x4, the quantum tracking for 4x4, and also we're going to do the classic backtracking to 4x4 and try to compare them. And for now, it's really hard. It's really hard to create quantum tracking algorithm here. So hopefully we will be able to convert that to the open quantum, and kind of bring back to the classic engine, and try to synthesize it, how we get a better different circuits. That's our goal here. So by end of the semester, we should be able to compare them and try to figure out, also some theoretical analysis. And we already there. I mean, the theoretical is easy. I mean, it's not easy, but it's easier than actually implement. So our goal would be try to implement them and improve them and compare results. So that's our goal here. So I guess I miss my teammate. They don't even show up here, right? So I'm okay. So they don't even, I mean, I went to everyone support them, right? They don't even show up here today. So that's okay. Thanks.
So the project is about quantum backtracking. You are working in this direction, but the other two just...
No, I'm direct here. I'm direct here, right? Quantum backtracking. That's what I'm doing.
But the other two are still active, but working different subjects.
The Crystal, she is wrapped up with all. Say you want to get the optimized classic, not even backtracking, the classic algorithm. I'm not sure what's doing here. I mean, want a meeting here, they never show up, so I'm okay. So, and the bench, he tried to implement I'm not sure what he's doing there. He tried to tell me he tried to implement the Benow's quantum walk algorithm here. That's even not even come to the quantum backtracking. Is something basically the quantum walk kind of adopt the one by the one first paper actually quantum backtracking kind of adopt the Benow's quantum walk to make it better. But he goes back. I'm not what he's doing there. I give him a presentation. I share them. Say give me updates. They don't give any updates. I mean, so I try to put their stuff there, but they don't give any information for what they're doing there. So I'm not sure. I just probably if that not happen here, I will have my own group. So
okay, can you send this also your slide, please?
Yeah, I'm gonna fix this project.
Your slide to me.
What?
Can you send your slides to me in the Slack?
I will. Yeah, I sent that to you in the DM.
Okay.
Yeah.
It seems I should contact your group members. So let's see.
And also, I don't think the Eric is much help either. So I mean, it's he talked to Crystal out in the travel, and the thing is not even involved with the quantum tracking at all. Something other stuff. So.
This group looks strong, and they said, if you remember, you can continue without a mentor, but it seems some mentor.
No, I can, but not. I don't think other people can.
Okay.
I sent you my slides, so I'm okay. I'm sure to feel busy myself, so it's not a big deal. Sorry for that. I'm complaining, but really they complain about me also.
Okay. Yeah, I should think because it's still course activities are under course.
Yeah. I try to help. I mean, yeah. So
talk with others as well. Yeah, thanks.
Yeah, thank
Any
you.
question for David? Okay, David, thank you. We can continue with 26, project 26. There is educators and minds. Minds are still active or?
Educators.
Yeah,
Alvaro, do you know about the other group?
yeah. I'm from another group.
Maybe we can first hear the other group.
The other group,
Okay.
okay.
Minds 26. Minds.
Okay. Yeah, I will share my screen.
So you are alone, Rishi?
Yeah, so we were three, but in last week, other two members are not like they are. I'm not
They
sure they are
disappeared.
continuing on. Yeah.
Rishi, first week was okay, but after 2 weeks the progress were low. Okay, let's listen you. You have 10 minutes, okay?
Yeah. Okay. So in last 2 weeks, we worked on we in last presentation only we presented introduction to web IDE and SDK of Classic, but there was barely stated example. Furthermore, we added GHJ state uniform distribution and other state preparation in both Classic web IDE and Classic SDK notebook. Also in both notebooks, I thought that I will add some quizzes, but I found adding tasks which are related to above given examples would be more appropriate. So in notebook and in a web IDE notebook and SDK notebook added tasks related to above examples, and also made video on introduction to web IDE and SDK. So these are the links for them. And after that, I'm working on dual algorithm. So for that, I started with oracles, and after that, my plan is to make 2 more notebooks on phase kickback and dual algorithm and Josa algorithm. So total 3 more.
Rishi, can you open one of the videos? Maybe we can see quickly.
Yes, sure. I shared them. So in web
Just
IDE part,
randomly go further.
yeah. So I started with state preparation circuit,
So
and
you
then
prepare this, Rishi, correct?
yes,
Okay.
yeah. So I covered all basic state preparation in IDE, and then I also tried to show how we can play with errors to increase and decrease width and depth of circuit, and
Okay,
yeah,
okay,
and
okay. Okay, you can continue with your presentation.
yeah. So in Oracle Notebook, I tried to cover it from scratch. Personally, when I was studying this algorithm, I just got stuck at Oracle and gave up. So I thought that I would make this as easy as to understand. So I covered what is Oracle and also linked video which describes why we have this structure of Oracles. So why we can't have just input and output. And also I implemented Oracle using Classic SDK. So Classic have built-in arithmetic Oracle, which I tried to implement, but since that Oracle is especially designed for Grover's algorithm, it was not working as expected. So took help of our mentor Nati, and he suggested to use arithmetic function instead of Oracle. So I tried with that function, and here is the result. So this is just example of Oracle. I just wanted to show how Oracle look like before actually jumping it and using it into a algorithm. So it's just take two inputs, and if it evaluates this expression correctly, then it gives 1 in output, else it gives 0 in output. And here I gave some observations which I will try to explain more better in upcoming video which I will make on Oracle. And at the end, I had a task related to Oracle. So here I have this code, and these are expressions. So people are expected to modify the code so that it satisfies these expressions, and similar to this is another task which I had added. And yeah, in upcoming week, I will complete notebooks on phase kickback and voice algorithm, and complete videos on these three topics which are related. And after that, my plan is to cover Grover's and Source.
Okay. What happened to other two members? Any idea?
No, I'm not sure if they will continue.
Okay, Rishi, that progress was fine. Just continue in the same direction because you need to do more progress. So like this, I don't have any specific question. If you really complete what you've shown, I think it will be fine, including videos.
Yeah. And also,
Yes.
after completing this, I would like to go back to introductory notebooks and make them more like better, so that if someone is coming from software background, they can easily catch up with classic. So
Yeah,
yeah, once this is
that would be nice. Yes, yes.
I will try to go to basic sheets
Mm,
then.
We have kind
Yeah.
of 1 month, so you should do more. That's I'm trying to tell.
Yeah.
Okay,
Yeah.
thank you.
Thanks.
Any question for Rishi? Okay, thanks, Rishi.
Yeah. Thanks.
And educators, Alvaro.
Yes. Yes, I am here. Miss Mancula, me. Well, I will share my screen.
Yes, please.
Share. Okay. Here we are three now, Asu, Mancula, and me. The
There is one
news
dropout,
about,
yes?
yeah, okay.
There
What?
is one dropout. Ricardo is dropped.
Two,
Correct?
Ricardo and Denise. Denise
also,
Denise,
yes. Denise also.
yes.
Okay, Alvaro, you have
We
10 minutes.
we are three now.
Thank
Okay.
you.
In regards to the methodology, in the last intern meeting with the mentor, we agree to include more ideas about the constraints, about the exercise showing in all the notebooks, exercise showing how to include constraints and observe the circuits generated, the different circuits, how to optimize the circuits. Okay, here are the new notebooks, and here is the author, the person who made each notebook. Quantum phase estimation is complete with exercise and solutions. A first version of Simon and Deutsch and Grover. I can show you, this is Deutsch. Mancula is here. She did this notebook. This notebook is a introduction, a theoretical introduction. The next part will be the execution in the classic platform and showing the circuits and all the stuff. We here have the quantum phase estimation notebook is completed. This was done based on the tutorial, the classic tutorial, but we demonstrate with a lot of matrices how to optimize the circuit, how to indicate how to operate with the matrices of different forms. So it's very instructive. Then we come here now. Quantum Fourier transform was last week. The Simon algorithm is new. Here we have a first introduction. The idea is not show the counts, the numbers, the details. The idea is to explain the principal things, the principal concepts, and to direct the student to detailed explanations in another courses in QNICL. Q course is of Q world, okay? Not include here all the details. Go to the classic platform, essentially. And we have about Grover, another initial notebook. In the other notebooks, we will include all of this about the state preparation. We will include the constraints, the idea of optimize the circuit by means of exercises. The idea is to include exercise saying, how can you improve this circuit with the classic platform? And the student must decide the constraint, test different constraints and observe the circuits, and use the platform in a very, very strong way. Regarding to the introduction about quantum computing, I think that we will refer to another courses, show concepts, the minimal concepts necessary to go to the platform and operate. Not all the calculation, the details, because the idea is that this is a way to use the platform to understand the algorithms, testing, interacting with the platform, essentially. So I think that we will short not put every explanations, the detailed explanations. Well, I think it is so. That's all. Next steps. We have not developed yet interactive videos. We will develop some videos, and the things that are pending are this: complete Grover, Deutsch, and Simon. Okay.
Okay, thank you, Alvaro. So basically, both groups doing similar stuff, as I see. The other groups also like preparing similar notebooks, correct?
Yes, yes.
I don't know, maybe you can recruit Rishi for video, and it's also possible. If you think you can invite him and he can be single group, this is just suggestion. It's up to
Single
you.
group. Yes, maybe we talked about this with the mentor, but yes, maybe we
This is
can
just a
join.
suggestion.
We can join and use the yes. We
Because your
will
notebook,
talk to Nati and
yeah, your
we
notebook
will
looks better.
integrate both in only one group. Okay.
Yeah, because your
Very
notebook
good.
looks better. But Rishi also just started recording.
Yes.
Maybe it can be nice. This is just a suggestion. Just let me know if you do such a change. Overall, yeah, good. Thank you. I don't have any question from the audience. Okay, thanks, Alvaro. Great.
Okay, see you.
Okay, and I think now we have 21, project 21.
Yes, sir. I'm going to share my screen. There's not very many slides as mentioned. Our team met. We're down to 4 people. So our team met to prepare this presentation. And I'll go ahead and share my screen now. Just a second.
Bill?
Yes. I'm going to share my screen now. Share screen. Just tell me if you see it.
No, not yet.
Oh, okay. I can share.
Something is coming, I guess. So, Bill?
Yes, do you see it?
Yes, I see it. And who contributed this presentation?
Oh, yes. So on the next slide, we have Wally. We met a couple times. Me, Tugba, Rajiv, we met with our advisor as well to go over and prepare the presentation.
Okay,
so,
now single group 4 people, correct?
Yes, that's correct. Yeah, so it's a single group now. These are the 4 people that are sort of left.
Okay.
Okay.
Floor is yours, 10 minutes.
Yes. Okay. So then, so what we're looking to do initially is execute Chasm code on Classic. This is the way we can call on Classic to execute code in order to integrate MIDIC. So one of the first things that we had to do, we talked a little bit about this last presentation, but there's 2 methods. One is documented within the Classic documentation page. And so I put a link there in case anyone wants to visit it. The second method is using an API wrapper or an API call that Classic exposes. It's not directly exposed, meaning there's no documentation, but our advisor provided some information on how to use it. It is asynchronous, so we had to utilize an extra library called async.io in order to make the call. If you notice there, we're pulling in the API wrapper from Classic, and then we call get generated circuit from Chasm. So we have to provide a Chasm string, which is basically a string of Chasm code. We had 2 examples that we used. One was from Chasm generated from Qiskit, and then one was from Chasm generated through the Classic SDK, or the platform, should I say. And we were able to work with both. There was an issue that we had initially, but we were able to overcome that. We actually had to look at some of the code, the Classic code, and search for some information. Again, since there's not very much documentation, we went ahead and pulled down the libraries and started looking through them. These are standard Python libraries for the Classic SDK. So we have as mentioned, we have two methods to get Chasm. This particular file here, for example, was from challenge 1 of the bootcamp. We're able to run it through Qiskit to generate a Chasm file, but we can also just read it directly into our Python code. And this is directly from Classic, so we can bypass Qiskit. But initially, since we weren't able to use the Classic function until we figured out how to overcome some problem we had, we were using Qiskit to generate our Chasm. So the next step that we did is we essentially were able to execute a circuit. So here we pulled in this particular circuit from the bootcamp, challenge 1. We read it in, we converted it to a circuit using Classic's SDK. And then we were able to actually get a result. So now we can execute the Chasm code against a Classic platform using the execute function, which you see here. Now the results that we were able to retrieve, we're still going through them, but essentially there's many facets to the results. So this is a huge piece of data, but we're able to get all kinds of information back out from Classic or the Classic platform. So part of our next job is to basically review what's being returned, break it down. And there are methods for that. If you notice here, you can get the results per value, you can get qubit counts, you can get information related just to a specific qubit. So we're going to go and basically break this down and see what kind of information we can draw. It is JSON code, so we should be able to parse it out. So the next step that we want to do after this is to utilize MIDIC for error mitigation. In other words, pull down the code from Classic, run it through MIDIC libraries, and then resubmit it to the Classic execute function. And that's what we're working on now. We actually got started on it recently. So what we did is we took what is currently included in MIDIC, the MIDIC example that has what's called the IBM executor or Qiskit executor. So we replaced it with this Classic executor. And all it is basically we'll run the Chasm code against Classic versus IBM's backends initially. And then we're going to use Classic to run it against IBM backends. But initially, right now, we're just running it against a simulator. So the intent of this is now that we've replaced this, we should now be able to introduce some MIDIC modified circuits. And so I should have, oh, let me see, I think I missed a, oh, yeah, I missed one particular slide that we had in relation to this. Let me see if I have it here. I apologize. Oh no, that's the last slide. So essentially what we've done now is, again, we're using Jupyter Notebooks to execute and now call our function, but we have not yet introduced MIDIC code to it. And that's what we're doing this week. And that's the end of the presentation. Thank you.
Okay, doesn't sound like too much progress, if I am not mistaken. Bill, what do you think the main contribution of this project will be at the end?
Well, what we hope to do is it will, we're hoping that we can take the MIDIC libraries. For example, ZNE is the first one that we're trying to do. And since we're going to be using the Classic platform to to pass circuits that have been processed through, say, the ZNE or the DDD techniques, error mitigation techniques. The idea is to process them using MIDIC through a Python script and then run them to Classic and let Classic do the processing. And that's the extent of what we can do, I think, at this point. That would be the goal, is essentially to be able to utilize Classic to actually execute the circuits that are modified using MIDIC.
What Classic has now at the moment?
It doesn't have any error correction features.
Error mitigation techniques.
I'm sorry, yes, error mitigation features. All it has is the ability to specify a bit flip option. And there is no way to introduce any error, which is you know, something that you can't do currently in Classic. And that was pointed out by our advisor. So that's why we're having to go through utilizing the external SDK to at least make some discovery or do some discovery on what could be done.
So basically, you want, if somebody works with Classic, they should be able to use MIDIC automatically, something like this.
That would be the ideal, but currently that they'd have to use the Classic SDK. Yes, so I think in the end, what we would end up producing would be something that could be used on the MIDIC side. So right now, MIDIC has examples for Circ, Qiskit, and a few other SDKs. Essentially, we'd be creating a new executor that could be utilized with MIDIC. So this would be something that would probably target more on the MIDIC side, where somebody could say, "Oh, I'm working with Classic or Classic. How can I run my circuits against Classic?" And so we'd have an executor already listed there. So there's already some, as mentioned, for Circ and for Qiskit, and maybe one or two other frameworks. This would just be an additional framework that could be used with MIDIC.
So basically, you want to add something to MIDIC in this sense.
That sounds like what we're essentially doing here, is coming up with a way to execute circuits that are run through, say, ZNE, MIDIC ZNE library, and then execute that against Classic.
Classic has its own simulator also.
As a what?
Its own simulator, or Classic
Yes, well,
only using IBM, etc.
Yes, but our target is to actually use IBM's hardware through Classic.
I mean, if MIDIC is already accessing IBM directly.
Yes, you understand that correctly. Yeah.
And why we are putting Classic in the middle, kind of like, it sounds like you should do something from maybe Classic side, not MIDIC side.
Yes, that's a discussion that we had with our advisor, but that would require us to actually make changes to Classic, and that didn't seem within the scope of the time that we had. You know, that would be our first goal, and I think the biggest blocker would be that there's no way to introduce any error currently in Classic. That was identified early on. So
but after 1 month, for example, when we finish all these collective meetings, do you think there will be something concrete in your group outcome?
I mean, it could be something that we could propose, but rather, you know, being able to build it, I don't know. We don't have access to the, you know, to the source code or to the libraries that are actually used for Classic, aside from downloading, but you know, that would take modification and then
what I am trying to understand, your group will really like produce some outputs, or it's more like understanding, etc.
I would say, yeah, it's more like understanding and not necessarily putting, you know, creating an output. I think it was a lofty goal from the beginning. The only way that we'd be able to introduce error mitigation or MIDIC directly into Classic is to inject it at the library level. In other words, we'd have to clone Classic Classic's SDK and then make modifications to it. You know, by
what your advisor is saying.
This was the path that that our advisor has so far recommended, which is essentially replacing the current executor function with one that runs against Classic.
Okay, I mean, you know, this is a project course, and it will be good to, like, this is not like teaching course. Okay, it's good that you are learning, of course, but there should be some outcomes as well. This is my concern now.
Yeah.
I hope you understood my point.
No, I do. I understand your point very well.
It will be nice to have like, okay, this is like some outcomes we produced.
So then maybe we can work towards actually making changes to the Classic platform, but we would only be able to.
You should talk with your mentor. I mean, if your mentor will be fine, this path will be still fine, but you should just discuss with him.
Okay.
Okay, because we are now close to end, and I don't see like there are some outcomes. Maybe I am missing some point, but I don't feel like this. Okay, any other question or comment for this group? I mean, now we are 4 people, still there is 1 month. Maybe you can push little, Bill, okay?
Okay, sounds good.
Yeah, thank you. I think this is also our last group for today. Yeah, thank you, everyone. As I said, we will finish course like second half of January as scheduled. But maybe for this writing, you remember there was also writing activity. Maybe we can keep it short and ask more progress, because some group already missed some weeks and some groups have less progress. So we should, yeah, find some balance. We still have at least 1 month. Okay, please use your month and like to have some good outcomes. When it's time to present at the end or to write this short paper, you know, there should be something. Okay, before closing, any question or remark?
So question here. What's the requirement for the final paper? What we need to do there? I mean, you have up to 4 pages, right? What's
Up to
required
4
there?
pages. It's just an activity to write down what you have done. You will present it at that, but also maybe in a written form, you can nicely put.
Yeah. So what's the requirement to finish it, to pass the course?
Pass a course, there is this complicated formula on the web.
Okay. So the only problem here, we don't know any of our score, right? I did everything.
I am saying.
Yeah. Because we don't have mental grade our paper, right? So I'm not sure how much we grades got, right? I mean, it's okay. We're gonna pass. We're just curious, yeah.
We are giving verbal, like when I said more work, that means it's low.
Okay.
And when I say you should do more progress, probably it means it's not enough yet.
Yeah, we wish have some comments in our
But I'm always doing comments.
Yeah, thanks.
Verbal comment. Your group was fine, but now I don't understand what is happening. It was one of the example group, but now 3 different directions. We should resolve how to handle it. Okay, any other question or comments before closing? Okay, thank you everyone, and keep in touch in Slack.